So I ended yesterday's lecture by introducing the linear category. So we started from a more familiar paraplectic Brouwer category, and by more or less taking the idempotent completion, we obtained a bigger category, the paraplectic linear category, which is still a monoidal category. And what I didn't mention yesterday, but is kind of immediate from construction, is that we still get a monoidal functor from this category to the category of finite dimensional modules over the paraplectic Lie superalgebra Fn. So for any n, of course, still. So for instance, this object, so that's just the number 1, and as an element of its an idempotent in its anamorphism algebra, there's only one thing to take. One strand, the identity, gets mapped to the natural representation, of course. So this is just some monoidal functor, and its image corresponds to all modules which appear as direct summands in tensor powers. So the first thing I want to discuss about the paraplectic linear category is the indecomposable objects in that category. Because remember, one of the motivations I gave to introduce this category is to classify indecomposable objects, indecomposable modules appearing in tensor powers. So we start by classifying the indecomposable objects in the linear category. So in general, we saw objects roll isomorphic to objects of this form, where we have some summation, some formal summation, some direct sum of objects given by integers and idempotents in the corresponding paraplectic Brouwer algebra. So if we want to look at indecomposable objects, of course we can restrict to simply objects like this, some integer r and some idempotent in the corresponding paraplectic Brouwer algebra, and even just restrict to the case where this idempotent E is a primitive idempotent. Because by construction this category is idempotent split. So if we would take a non-primitive idempotent that we can write as a sum, that object would be isomorphic to the direct sum of those two idempotents. So the indecomposable objects are given by integers and primitive idempotents in the paraplectic Brouwer algebra. We understand more or less primitive idempotents in the Brouwer algebra because we know the classification of their simple modules. So we have an immediate relation between indecomposable objects in this category and simple or projective modules over paraplectic Brouwer algebras. And they were always labeled by partitions. So of course some partition could appear in description of AR, but also AR plus 2, AR plus 4, etc. So it shouldn't be surprising that those different appearances of the same partition will lead to isomorphic objects here. The reason I say it shouldn't be surprising is because this is more or less the same statement as saying that CR doesn't really have more objects than AR, it's Morita equivalent. Because what we did there, CR was some bigger algebra in the paraplectic Brouwer category, consisting of anamorphism algebras for different integers, and it didn't lead to more modules. So basically that meant that we in the Brouwer category or in the linear category we can identify those same partitions for different Brouwer algebras. So for instance we can, for any partition So I use this notation for the set of all partitions. So for any partition lambda, we just consider a corresponding primitive idempotent in the minimal paraplectic Brouwer algebra for which that makes sense. So we just take the size of the partition, look at the corresponding paraplectic Brouwer algebra. Then that partition has some indecomposable projective object labeled by it. We take the corresponding primitive idempotent and create an object in there. So this is just one choice. We could have also taken something in R plus 2. But the theorem is that this construction gives us a bijection between the set of partitions and the set of isomorphism classes of indecomposable objects. So in some sense, you could see the paraplectic linear category, or at least its category algebra, as some limit of the algebra CR that we had before, which is another way of viewing this statement. Another way of formulating this is in terms of the split Grothendieck group. So this is, by definition, so this is like an analog of the actual Grothendieck group for abelian categories, which makes sense for additive categories. So that's just the abelian group generated by isomorphism classes of objects in the category with relation given by this equation. So if some object is a direct sum of two other objects, then in the split Grothendieck group we say that its image is equal to the sum of those images. So in other words, this is just a free abelian group generated by the isomorphism classes of the indecomposable objects. It's just a more complicated way of saying that. So then we have that this group is isomorphic, let's say, as a Z module to the space of partitions, say the the group or the Z module given by Z linear combinations of partitions. It's just a reformulation of that statement, which will be slightly more useful later on. So the fundamental question we want to study, and I'll justify later why this is what we want to ask ourselves, is we want to classify thick ideals in this category. So thick ideals, or thick tensor ideals, is better. Because a tensor ideal in a monoidal category is not an ideal in most conventional sense of a category. So it's strictly speaking not an ideal in a category. But it is a full additive subcategory let's say I in PD, which is on the one hand what you might call thick, in the sense that if the direct sum of x and y is in the ideal, then x and y themselves are both in there as well. And it is an ideal for the tensor in the sense that if x is in the ideal, then the tensor product of x with anything else is still in the ideal. So here we work with something which is actually symmetric or braided, so there's no notion of left or right ideal. Otherwise you could, of course, just have the analogs of all that. So because by assumption it's an additive thick subcategory, it suffices to classify which indecomposable objects are in I. And then the entire category is just whatever is additively generated by those indecomposables. So it's really quite some rather a rough structure. So that's the first thing that I want to discuss, is how to obtain the classification of the thick ideals, the thick tensor ideals.
So you have this functor f. This is going from this category PD to Fn. So here it's so does the image include all irreducibles of Fn with such the highest weight is conditional? Will it include those?
Well, for instance, what we do know is that the image includes all projective modules. But it's hard to say which simples are in there, for instance, or if there are simples in there.
Yeah, if there are direct summons.
Yeah. So the image is all direct summons of tensor powers.
Right. I'm just wondering whether you know that all this irreducible can be obtained as a direct summon of tensor powers. So that was my question, actually.
That seems very unlikely, but yeah, there might be some exceptional cases. But I wouldn't expect too many to appear. kind of projectives, they appear all, and simples are the opposite of the terms of that. So
I think always you're like in B tensor V, right? I don't think you can get.
there are no simples in there. No.
Yeah, except probably the true appears as a summand.
Not as a summand.
Not as a summand. Cool.
No.
Cool.
Yeah. Because.
Oh no, never been summand. That's right. It's a non-split extension. Yeah, that's
Yeah.
right.
So this is as far as it splits.
That's right, but then you have.
And the trivial appears as the top
Twice,
of
right.
one and as a socle of one, which is the combination of a cup and a cap, give a morphism, but it doesn't split off. Okay, so in order to attack this question of the thick tensor ideals, we studied the following functor on this category, which we call just T. And it is just given as the functor which takes the tensor with this particular incomposable object. So this is of course just this object here. So this is actually an object already in the paraplectic Brouwer category, and it is an object that generates everything. If we just take over and over the tensor product of this object with itself, we had all the objects in the paraplectic Brouwer category. And then this category is just the idempotent completion, so all objects in there appear as direct summands of this. So, in other words, the thick ideals are just the thick, full additive subcategories preserved by T. So that just means the second condition here, that x times y needs to be in the ideal for any y, can be replaced by just using that particular object instead of arbitrary y. So on objects, this functor, so if we take some object as before, R, and some idempotent in AR, is given by the general formula that I presented yesterday as this object. So you get R plus 1 and some idempotent, which is just the products of the old idempotent, and just one strand. One propagating line. And the first thing we'll do is construct some natural transformation of that functor. So if we set x to be this particular object, then we want to find for any such x some morphism in the endomorphism algebra of T of x, which should then be natural in x, etc. So this is by definition and plugging in this form here. This endomorphism algebra is given by this idempotent truncation of the paraplectic Brouwer algebra. So this was how we defined definitions in the paraplectic Deligne category. And then what we can do is to take one particular element in there, namely the image of the juicy Murphy element. So this is the last of the chain of juicy Murphy elements that we have for this algebra. It is in there. And then it is not very difficult to verify that this actually leads to a family of morphisms which constitute a natural transformation. Precisely because this one commutes with the subalgebra AR. A statement which can be generalized slightly such that it is really what you need. But so we need more or less that this one commutes with morphisms from X to some different Y, gives a nice commuting diagram. And the reason that that diagram commutes is just the reason that this one commutes with paraplectic Brouwer algebras, which are fit in on this part of the tensor product. So there's nothing much to check there. So this relation rather easily, because morphisms in this category are basically given by elements of paraplectic Brouwer algebras. This gives us a natural transformation. So from T to itself. And it's not completely obvious because it's not an abelian category, but we can use this to construct a decomposition of this functor into eigenvalues corresponding to that natural transformation. So it took us a little bit before we could figure out how to define it rigorously, so I won't go into details, but it is possible. So this allows to decompose this functor into functors Tj for any integer j. Well, if you accept that they were integers for the paraplectic Brouwer algebra, then it is more or less obvious from that. So we've seen the action of juicy Murphy elements on the cell modules, and they were all integers. And projective modules have filtration by cell modules, so any module, the action must be given by integers, and then it follows from that. But yeah, a priori.
For the juicy Murphy element,
yeah, well, for the symmetric group, it's also true. So.
Is that a completely trivial statement? I'm not sure.
Well, it depends. Yeah, I mean, it depends on your definition. You could have added a non-integer constant to everything, and it would still work. But yeah, I don't know. Where we just calculated the action on the cell modules, and we got integers. So,
yeah.
I don't know if you could prove, before you prove what the eigenvalues are, that they are integers. I don't know if you could prove it like that, but we just calculated them and they were all integers. Okay. So then, for some integer z and a pair of partitions, we define some natural number, so aj nu k kappa. By this relation, we say that Tj acting on this indecomposable object has this expression. So what we get here must decompose into a number of indecomposable objects. We just keep track of the multiplicities and define some numbers A in that way. So if we understand these numbers in particular, we know what falls out of that functor and we can classify thick ideals. And it turns out that we can describe this, these numbers, or the matrix labeled by partitions, columns and rows labeled by partitions, can be described by things we've already encountered. So that's this theorem. So this is to be interpreted as some matrix equation. So I leave out the indices, so I really regard this as a matrix. Columns and rows labeled by partitions. Then I have this matrix identity where the matrix C is given precisely by the multiplicities of the cell modules. So now I just introduce some R, which is big enough and of the correct parity, basically, so that this makes sense. So just take R big enough such that both partitions are bounded by it. And the matrix B also depends on J. Has entries 0 and 1. And we get 1 if mu is obtained from lambda either by adding a J box or if mu is obtained from lambda by removing a J minus 1 box. So by a J box or J minus 1 box, I mean a box with content J or J minus 1. Like we've seen. Okay.
We will change to another